session. But first, what we given by Davison Soper from Oregon University will be on one of the 3 lectures that he will give here is on QCD. So let's welcome David.
Well, thank you very much. It's a real pleasure to be here, and I thank the organizers for the invitation. I have 3. Thank you. I have 3 lectures about perturbative QCD. It's not intended for the experts. There are quite a number of real experts on QCD-like things in the audience, and I'm not going to try to address them. That would be at a much higher level. Rather, I'd like to address students, people who are not doing QCD-like things, and I'll just be very general and not at a particularly high level. But what I want to do is to tell you about some things that speakers at conferences and workshops who are giving technical talks, things that the speakers will assume everybody knows. So here's the place to find out what it is you should have known. So I'm going to talk about jets, and slides. Well, it doesn't matter too much. I had a drawing of a detector. So you think of Atlas or CMS detector at the LHC. If the beam's coming this way, then there's an azimuthal angle around like that. We call that phi. And then there's an angle in the direction of the beam from one beam over to the other, and normally you would call that theta, but people don't really use the angle theta. They use the pseudo-rapidity, which is minus the logarithm of the tangent of theta. That way, pseudo-rapidity, which is called eta, is 0 in the middle of the detector, and if you go toward one beam, it gets to be very big. Not so big because it's a logarithm. So there's 0, 1, 2, 3, 4, 5. 5 is sort of the end. And minus 2, minus 3, up to minus 5. So what you do is measure angles that way with eta and phi in the detector, and then you can measure for any particle, the transverse momentum of the particle. The momentum transverse to the beam axis. You can make a little graph. And here's how you make the graph. So I have eta, that was the pseudo-rapidity, and phi, the azimuthal angle. And then on the vertical axis, I can put transverse momentum. That's the absolute value of the transverse momentum of a particle, or say group together several particles that are coming into a little cell in eta and phi. So people can make a plot like that. They're called Lego plots because they look like they're little toys, Legos. And I think there's a disaster here because I'm missing every other slide. Is this thing working right? Maybe if I use the back and forth here. Yes. Oh. I don't know. This one says skip 2 slides. That doesn't make much sense. But here's my detector. Isn't it beautiful? Yeah. You can see that I don't really know what the detector looks like. There's the eta and the phi. Here's the Lego plot with nothing in it. here is what you see in an event, in some events. This is a rather rare event. But what you're seeing is that there's a lot of transverse momentum in a very small area in eta pi space. And over here, there's another bunch of a lot of transverse momentum. This is hundreds of GeV. Here's, they call it ET, that's transverse energy. It's the same as transverse momentum. So a lot of transverse momentum coming out in particles in a narrow angular region is called a jet. And that's the subject of this first talk, is just all about jets. So here, what we see is evidently two jets. Here's another event. This one has more. Depends on how you count it. Maybe there's 4 jets there. So what you see in actual events at the LHC is transverse momentum concentrated in a few narrow sprays of particles. And those you call jets. The event that I just put up here is the one with 2 jets. Now, these are kind of rare events. These are 1 out of 1,000 or 100,000 events. The LHCS it throws away most of the events it sees. Events in which the total amount of transverse momentum is big, hundreds of GeV, those are rare events. So if I sum the absolute values of transverse momentum of all the particles, sum the absolute values, not the vectors. If that comes out to be more than 100 GeV, that's a rare event. But not so rare. There's still millions of such events that have been accumulated. And whenever you look at such an event, it looks like the pictures I was showing. So like this one right here with some jets in it. It never happens that the transverse energy is spread all over the detector. They're always in jets. And why is that? So what I've done here is I've drawn a Feynman diagram here. And what's happened here is there's a quark coming in, another quark coming in, they're scattering and make something that goes out sideways and something goes out the other sideways at high transverse momentum. And then there's gluon emissions, and the gluons split into more gluons. That's a part-time shower, and I'll talk about it in the next lecture. But just look, say, right here. Suppose this gluon is labeled with momentum P1, and that one has P2. And P1 squared and P2 squared are both 0 in this approximation, so they're on shell. Then this gluon has momentum P1 plus P2. So just think about that from the point of view of Feynman diagrams. There's a denominator in when you write out what the Feynman diagram corresponds to. The formula is 1 over P1 plus P2 squared. And suppose P1 goes to 0. You think of it getting softer and softer and softer. If that happens, P1 goes to 0, it's 1 over P2 squared, but P2 squared is 0. So that 1 over P1 plus P2 squared goes to infinity. Similarly, if P2 goes to 0, then that denominator goes to infinity. And if P2 gets to be parallel to P1, so lambda is just a number. So P2 is parallel to P1, then 1 over P1 plus P2 squared is also going to infinity. It's just 1 over 1 plus lambda P1 squared, which is 1 over 0, which is infinity. So in all of those cases, we're getting a very, very large Feynman graph. So it must be very common to have either soft emissions, P1 goes to 0, P2 goes to 0, or to have collinear emissions where they're both collinear. If they're neither collinear nor soft, then it's sort of rare, but if it's emissions either collinear, if they're not collinear or soft, it's rare, but if they are collinear and soft, it's common. And therefore, you see right straight from the diagrams that you should have very frequently a whole bunch of particles here coming out parallel to each other. Well, some of the particles in the graph have very small momentum. If they have very small momentum, they're over here, even if they're small momentum wide angles, they're over here somewhere, but they're not making much of a blip in that graph. The ones with lots of momentum are always parallel. So you can see right straight from QCD diagrams that you expect to see sprays of full linear particles or jets. That was actually predicted before anybody dreamed of QCD by Bjorking, Berman, and Kogut in 1971. And I've just reproduced a picture from their paper. They didn't have QCD, but there was around at that time what's called the Parton model. Made up, it's usually credited mostly to Feynman, but Bjorking had a lot to do with it. One knew that proton contained small point-like things. We didn't know what they were, so they were just called partons, meaning something, a little particle, and parton meaning it's a part. And it was also known, and that was known from deeply elastic scattering, by the way. The experiments done at Stanford Linear Accelerator are just around this time, 1969 and 70. It was also known from Feynman's analysis that if a proton was made of partons, some of the partons carried a fairly big fraction of the proton's momentum if the proton was moving very fast. But if there was a fast-moving proton, some of the partons carried not so much, a tenth, a hundredth of the longitudinal momentum of the proton. Those, Feynman called them weak partons. So here's a little picture that Bjorking, Berman, and Kogut drew of proton-proton collision. And here's before the collision. There's 1, 2, 3, 4, 5 partons here that are in the right-moving proton. And here's a bunch of partons in the left-moving proton with carrying 10, 20 GeV of energy. That's before the collision. Now, 2 of those partons could collide and scatter at large transverse momentum. There was not known at that time QCD, so now we think they'd scatter by exchanging gluon, like in the diagram I drew. But at least they should scatter by exchanging a photon. And it was known because of deeply elastic electron scattering that partons did interact with photons. So at the very least, 2 partons could scatter by exchanging a photon, and then here's one of them and there's the other. They got a lot of transverse momentum, 12 GeV in this picture of transverse momentum. And now what would happen? So what these authors wrote was the isolated high PT partons will communicate with the weak partons, that's these guys here, by a cascade emission of partons. Okay, that's sort of a guess, but a very good guess. And if that happens, then here's how it comes out. All this one parton up here with 12 GeV of transverse momentum now splits into a bunch of partons whose total momentum is still 12 GeV, but each of them has less. And here's what happens to the other parton. And what are these things? That's a jet. That's a bunch of partons with momentum all in the same direction. Okay, so jets were a prediction from 1971, before anybody had QCD. And here's some experimental evidence. This is from electron-positron collisions at Petra Accelerator at DAISY in, this is early 80s. And this was shown at a conference in 1983. So this is the Lego plot, the first Lego plot, with the same kind we've seen before, except they use theta instead of eta. And what do you see? A lot of transverse momentum concentrated in small regions of angle space. And one of them, 2 concentrations, 3 concentrations. So that's an event with 3 jets. What happens is an electron-positron made a virtual photon, split into a quark-antiquark pair, and that emitted a gluon at a wide angle. That so quark and antiquark and a gluon made 3 jets. And there's just direct experimental evidence for it. You don't need any calculations, you don't need any Feynman diagrams, you just look at that picture and you can see what happened. Okay, so I'm going to talk about jets. I want to tell you a little about the coupling in QCD before we do that. At each vertex in a diagram, like here, there's a factor which is usually called G. That's the coupling. And G squared over 4 pi is usually called alpha strong. So what can you say about G? So just consider a Feynman diagram in which all the momenta flowing around are orders of Q. Q is maybe 100 GeVs. So this quark is carrying 100 GeV one way, and that quark is carrying 100 GeV the other way, and this gluon also is carrying somewhat, maybe half of 100 GeV, 50 GeV. Okay, so big momentum of order Q. But now suppose we consider some loop graphs that dress this thing out. So I just drew a loop graph. I was just mean, I drew a complicated loop graph. What's going to happen there? That loop means you do an integral, 2 integrals over momenta inside the loop. And when you do that kind of an integral, you write down what it is. It's d4k over k to the 4th. Momenta much bigger than q squared are important inside the integral in that diagram. In fact, the whole diagram, the integration is divergent, but so imagine we put a cutoff on the amount of momentum that's going into that loop. We just cut it off at some scale m. Then what's going to happen? So now this takes a lot of analysis, and we're certainly not going to do that here. But what happens is that you can get rid of that whole thing approximately, and all you have to do is change G. Change what goes at that vertex. So this big complicated thing with lots of stuff going on and very, very large momentum inside the loop, you can just get rid of it and just say you just change a factor here associated with the gluon emission. So now we've got a new value of alpha strong, but the new value of alpha strong is going to depend on what the Q was that's generally flowing around this graph. So the value of the alpha strong depends on what the scale is Q. And when you do that and add up a bunch of graphs, so here I add up one loop graph and then another 2 one-loop graphs in a row and so forth, what I find is that alpha strong of Q, the one that you have to adjust to fix up the graph so you can ignore all the complications, is alpha strong of M. That was the original alpha strong, where m is 10 to the 19th GeV, let us say, plus a certain constant called beta naught times log of q squared over m squared. And then that's times alpha strong squared. And then there's another one with 2 logs and alpha strong cubed, etc. And that all adds up to alpha strong of m, the alpha strong you started with, divided by 1 plus this beta naught alpha strong of m and log of q squared over m squared. What happens there? Now it's turned into something is quite a different shape. And it didn't really matter what m was. You can also change this the same thing as alpha strong of mz divided with an alpha strong of mz here. Either way you write it, as q squared gets to be bigger and bigger, alpha strong of q gets to be smaller and smaller, because the log of q squared is in the denominator, and because that's a plus sign. So we now have what's called the QCD running coupling, and it gets smaller as q, the scale of the graph, gets bigger. And that's a real effect. It's in Feynman diagrams, there's a bunch of algebra to do that, but it's also a physical effect that you can measure. So here's a famous starting graph Here's alpha strong of Q as measured by several different kinds of experiments at different values of Q. Q is on the horizontal axis. So Q of 100, these are experiments at left with 100 GeV of electron positrons hitting each other with 100 GeV of energy, and Q going down to 10, Q even going down to just a couple of GeV. The lowest one here is tau from tau lepton decays, measured there, because the tau mass is pretty small. So you measure alpha strong of Q at a bunch of values of Q, and you have a prediction to what it should be. That's the formula I just showed you, and they just match very nicely. Okay, so now we know about the running coupling, and there's a lesson from that. This part over here is called asymptotic freedom. That is, when you get to have large Qs, the coupling is less and less, so the quarks and gluons look more and more like free particles. But down here, for Q less smaller, then the coupling's getting bigger. And as you get down to smaller Q, then you're not doing very well with perturbation theory, because perturbation theory is an expansion in powers of alpha strong. So we're going to have to be careful about that. And now I'd like to talk about jet cross-sections. I consider, let's say, the cross-section to make one jet plus anything in a hadron-hadron collision. So the jet has transverse momentum pt. It has rapidity y, the rapidity and pseudo-rapidity, which I was calling eta, are just about the same thing. So you can think of y as minus log tan theta over 2. I could have had an azimuthal angle there too, but the one jet cross-section is independent of the azimuthal angle, so I didn't make a differential in that. So suppose we want to measure that. That's a cross-section you can measure. And it should be an inclusive cross-section, so we're going to measure the cross-section for one jet plus anything else. Maybe there's some more jets. Maybe there's a Z boson. Whatever, it doesn't matter. One jet plus anything else. There's experimental data on that from the LHC. This one's from Atlas, but CMS has similar data. So look what happens here. So it takes a little explanation. Here's PT of the jet, starting at 20-30 GeV and going up to 1 TeV. And here is cross-section. Now they've taken the cross-section measured in different bins of rapidity. So the top bunch of particles here, that's absolute value of rapidity less than 0.3. That's that kind of an angle, right in the middle of their detector. And they multiplied all their data by factors 10 to the 12, 10 to the 9, 10 to the 6, so they just spread them out over this graph. Okay, so we can just look at the lowest rapidity bin, y less than 0.3, that's these points here. And what do we see? Not the vertical axis. So this is starting off at 10 to the 19, 18, 17, 16, 15. There's lots of powers of 10 here. And as I go from 30 GeV to 1 TeV, the cross-section's dropping by, I'm not sure, 1, 2, 3, 4, 5, I don't know, 6 powers of 10. So dropping an awful lot. And the black points are the data that's measured by Atlas collaboration, and the little bars here are theory. That's a prediction from QCD. Using next to leading order perturbation theory, using, there's something called part-time distributions I'll talk about in a moment. So those are measured in other experiments, and using the value of alpha strong, which is measured to best at lab. So the theory is working just amazingly well for cross-sections falling by 6 orders of magnitude. Everything's agreeing. Of course, this is, if you really want to see if the theory is working well, it's best not to draw it on such a graph. You should draw a ratio of theory to experiment.
Do you use the pattern distribution or simultaneously adjusted to higher and higher energy, or we use the
I think this is using part-time distributions that do not involve this data. And I'll mention part-time distributions in just a little bit. But before I do mention part-time distributions, I have to mention jet definition. We need a definition. So I've tried to indicate it was sort of obvious. You've got a bunch of jets here, you can just see them. So you measure the transverse momentum of each of those jets, and that's how you get the cross-section in experiment. And you do the same thing in your theory and get the cross-section in theory. But how many jets are there here? Whoa, and that's so obvious. Look right here. Is this all one jet, or is that 3 different jets? You better be careful, you're going to get a different answer depending on whether you think that's one jet with some bigger transverse momentum, or 3 jets, each of which has a smaller transverse momentum. So if we want to be precise and use next to leading order perturbation theory, we better be careful about a jet definition. And that's what I'd like to talk about now for the next few minutes. When we measure, we need the jet definition. The jet definition has to be what we call infrared safe. That means it better not depend on small q² physics. So here's this sort of picture we were looking at before. Suppose that P2 here is nearly 0, or P2, suppose P2 is nearly 0, and suppose P1 is almost collinear to P3, then effectively that coupling constant right there and this one are big. And if they're big, then we better not be using perturbation theory to try to get the cross-section for that. So when perturbation theory is breaking down, we're out of luck on using our theory. So what are we going to do? What we better be sure of is that the definition of the jet is such that when P2 gets to be 0, or when P1 gets to be parallel with P3, that the jet doesn't change. So all this stuff all together here could be all of that stuff together could be a jet, but I better get the same jet if one particle spits off another particle with 0 momentum, or if 2 partons become parallel. And that property is called infrared safety. So to state it a little more formally, what we're going to use to make a jet definition is a bunch of particles. So supposing particles with momentum P1, P2, P3 up to Pn. That's a fairly large number of particles. And out of those particles, we're going to have some definition that says I've got 3 jets in my vect. So N equals then 3 jets. And there's going to be some algorithm that tells me what jets I get, what particles make up my jets. So if any of those PIs becomes very small, we should get the same jets if we just leave that particle out. And if 2 of the particles, I and J, become collinear, then we should get the same jet if we replace PI and PJ by just 1 particle with momentum PI plus PJ. So that's the property we need for a jet definition, and it's called infrared safety. And what's the physical meaning of that? Here's what you have at the lowest level in the Feynman diagram, say 3 partons coming out. Here's what you finally get after the partons have